Well, I'm going to record a video solution to the static equilibrium problem requested by a student. Okay, so let's take a look at this problem for static equilibrium. This is a question from our practice exam. So we have a person standing on a ladder. Okay, so let's draw the free body diagram. So this is the wall. This is the floor. And we have a ladder leaning against the wall. Okay, so it says this ladder has its own mass, which means the ladder has weight, gravity, and it's going to be exactly halfway through. So if this entire ladder is distance d, this is at d over 2, you have the mass of the ladder times little g. So that's the weight of the ladder. What other forces are there? There's a person standing on the ladder 1/3 of the way. So somewhere around here, somewhere around about 1/3 of the way, right? There's a person. So which means we should draw the weight of the person. MP person, MPG. What else information is given? It's telling us the angle is theta with respect to the floor. And let's add all the other possible forces. First of all, right, you have it's leaning on it's putting on the floor, so there must be a normal force from the floor upward. It's leaning on the wall, right? So there must be a normal force to the left because the wall is perpendicular. Normal force is always perpendicular to the surface. So the force from the wall, this is also a normal force, but we're going to call it F wall just so we differentiate from the other normal force. It tells us there is no friction between the ladder and the wall, so which means there isn't any force in this direction, so there's no friction here, but there is a friction with respect to the floor. And what direction is that friction? You can see the force on the wall is to the left, so there has to be a force to the right to balance it, so that must be the static friction from the floor, and we call that Fs. So this is all our free body diagram. Now we could solve for the minimum coefficient of friction between the floor and the ladder. So this information is telling us what is the minimum surface required, minimum μs required out of the surface. So that it contains a information is the static friction must have been at its maximum value. And the maximum value of static friction is mu times n, normal force. So that information is included in this sentence. So to solve a static equilibrium problem, we either we would use these two equations. Sum of the forces is 0, sum of the torque is equal to 0. Okay, it doesn't matter in which order you use them. Eventually you'll be able to solve for everything. We could start with this one. Sum of the force is equal to 0. So we can see the vertical direction, you have normal force, then upward, you have the person's weight downward, weight of the ladder downward. They should add up to be 0. So this gives you the normal force right away, MP plus M1 G. We could also say, well, the force of the wall and the static friction will be equal, but that's not very useful for this problem. So we have this for now, and then now let's use the other torque equation. The torque add up to be 0. Okay, so we need to choose a rotational axis. And where do we put it? We don't want to put it here because that would eliminate information about friction. And we want to solve for static friction coefficient, right? So we don't want to eliminate that force, but we could put it here. We could choose to place our rotational axes to be at the wall and view all the torque relative to that point, because that will get rid of the force from the wall. And I don't care about the force from the wall because it's an unknown force and I can get rid of it and also don't need to solve for it. So relative to this point, which is our rotational axis, let's look at all the torque from the other forces. So how many forces we have? We have force from the normal force, force from the person, force from the ladder, force from friction, and they need to add up to be 0. When adding them up, let's think about its directions. So we know what to put positive or negative signs for these torque. So relative to the rotational axis, this point, relative to this point, let's look at in what direction these forces are attempting to rotate the ladder. The normal force is attempting to rotate the ladder clockwise, right? So that would be negative. The weight from the person is attempting to rotate the ladder counterclockwise, which is positive. The same for the weight of the ladder, and also the same for static friction. Static friction attempting to rotate the ladder counterclockwise, positive. Okay, so having figured out the sign, we can now expand these torques. Torque from the normal force. So let's look at, actually, let's look at this one first. Okay, so this one, friction is here, and it's at a distance d, right? From where the force is to where the rotational axis is, that's distance d. And the angle between them is theta. So torque is R cross F. Magnitude of the torque is R times F times sine theta. Theta is the angle between R and F. So in this case, it's clear. It's going to be D times F times sine theta. So I could work out this force, this torque, to be friction times D times sine theta. And we already know it's positive. So here we only worry about its magnitude. And next, let's do the force with the weight. So let's look at the picture. So this is theta. Weight of the person is 1/3 of the way in. So from this force to this rotational axis, there is a distance of 2/3 of d. That's r. And the angle between this and r, right? The angle between this r and the weight is this angle. That would be 90 degrees minus theta. So when you do r cross F, you have R times F force times sine of the angle between R and F, which is 90 degrees minus theta for this vertical weight here. And that becomes cosine theta. So I should expand this torque into mpg 2/3d cosine theta. Next is the weight of the person. Oh, sorry, the weight of the ladder. That's very similar to the weight of the person, except it's at a distance 1/2d away from the rotational axis, and it also should have an angle of sine 90 degrees minus theta becomes cosine theta. The same goes for normal force, because normal force is also in the vertical direction. The normal force has a distance d away, and the angle is the same, cosine theta, but normal force is the negative torque, so negative sine. So here we're able to find an equation that has the static friction force in it, and we try to solve for it. And we're trying to solve for mu's of s. So let's plug in the static friction as in mu times n, because we know right now it's at its maximum value if we want to find the minimum coefficient. So mu times normal force n times d sine theta minus nd cosine theta plus mpg 2/3 d cosine theta plus m1g 1/2 d cosine theta is equal to 0. We could plug in our normal force. Normal force has already been solved in the previous equation, so you can plug in normal force and solve for mu. Okay, so we have plug in normal force. So we have mu of s times mp plus m1 d sine theta minus mp plus m1 d cosine theta plus mpg 2/3 d cosine plus m1g 1/2 d cosine is equal to 0. So mu of s is equal to negative mp g. Well, we can bring the g and d, the common terms outside. G d cosine theta 2/3 mp plus 1/2 m1 minus sign, because move it to the other side of the equation, divided by, you have a common term. Sorry, here you should have, this should be g. Now we add the g here. Divided by mp plus m1, and we have gd all right, gd sine theta. Oh, sorry, I think there is something wrong here. mp Okay, so okay, so GD is the okay, MP M1 GD. Okay, sorry, made a mistake. On the numerator. Oops. On the numerator, I should add this term. Just forgot about it. MP plus M1 G E cosine theta. Okay. And divided by MP plus M1 GD sine theta. And that's clean up the top, become GD cosine theta 1/3 MP plus 1/2 M1 divided by GD sine theta MP plus M1 and cancel GD cotangent theta 1/3 MP plus 1/2 M1 divided by MP plus M1. So at this point, we finish solving the mu in terms of the known quantity. Theta is given, MP and M1 is given. So at this point, we've finished solving the mu.